Hello and welcome to yet another lecture on chemical engineering thermodynamics. Today we shall discuss about adiabatic processes. The fluid is an ideal gas. Now, what exactly is an adiabatic process? In an adiabatic process, the heat given is zero. That is, the heat given or the heat taken by the process from the process is zero. Now we are going to study the adiabatic process on ideal gases. The model for the ideal gas is PV is equal to RT, where the temperature is in Kelvin. R, the universal gas constant, is in kilojoule per kmol Kelvin. The volume is in meter cube per kilomole, and the pressure is in kilopascals. We are also aware that for an ideal gas, Cp minus Cv is equal to R. That is, the heat capacity at constant pressure minus the heat capacity at constant volume is equal to R. Now let's analyze this process thoroughly. So let's go to the first law equation for closed systems, which is nothing but du cap, that is internal energy per unit mole, is equal to dq, that is the heat transaction of the process, minus P into dV hat, where V hat is nothing but the volume per unit mole. Now, we do know that for any process, du is equal to Cv into dt. And also for this process, that is an adiabatic process, dq is equal to 0. Therefore, we have du equal to Cv dt is equal to minus P dV hat. Adding dPV on both sides, we get dH is equal to VTP, since H is equal to U plus PV. Therefore, we divide equation number 2 with equation number 1, and we get dH by du is equal to V dP minus P dV, which is but nothing but equal to Cp dt upon Cv dt, which is again equal to V dP minus P dV. Well, we need not write the last one. It's actually is equal to Cp by CV. So we have Cp by Cv for an ideal gas is written as gamma. This is equal to minus V dP upon P dV. We can write this as minus gamma dV by V is equal to dP by P. Therefore, we get minus gamma into ln plus ln K is equal to ln P. Well, we can write the constant on both the sides. I would prefer writing the constant on the RHS. So let's remove the constant from here, the constant of integration from here, and write this as plus ln of K. So we can write this as minus ln of K is equal to ln of P plus gamma ln of V. Or we can write ln P V raised to gamma is equal to ln 1 by K, which can be written as ln K dash. Or we have PV raised to gamma is equal to K dash. In general, we write it as PV raised to gamma is equal to K. This is the law for an adiabatic process on an ideal gas. Now let's visualize how does this process look like. Let's draw our axis. This is our pressure axis, which is the y-axis, and this is our volume axis, which is our x-axis. So this is in meter cube per k-mole, and this is the pressure axis in kilopascals. Now let's assume that the fluid is initially at point number 1. Its pressure is P1, the volume is V1 hat, and the temperature is T1. The fluid is compressed to a pressure T2. So the process looks something like this. It's not exactly a straight line. So this is P2 and this is temperature T2. Now the isotherm passing through this, and there's an isotherm passing through this point. It should be noted that T2 will be greater than T1. Why? Because we have compressed it adiabatically, and this will increase the temperature. Many people have a question that is the equation P1 applicable to an adiabatic process? The answer is yes. This is equation of state, as it shows a relationship between the state variables. This is the equation for adiabatic process. So both these equations can be used. Now, an important conclusion that we can get out of this is, let's assume that the gas has gone from state 1 to state 2. Now, can we relate the temperatures to the pressures? We can, by using the equation of adiabatic process and the equation of state. We write down P1 V1 raised to gamma is equal to P2 V2 raised to gamma. We can write down P1 and replace V1 by the equation of state. Therefore, we can write it down as V1 can be written as V2 P2 by T2 into T1 by P1, the whole raised to gamma, is equal to P2 V2, the whole raised to gamma, the whole raised to gamma. It's here too. Now, this equation is P1 V2 the whole raised to gamma into P2 the whole raised to gamma upon T2 the whole raised to gamma into T1 the whole raised to gamma upon P1 the whole raised to gamma is equal to P2 V2 the whole raised to gamma. V2 raised to gamma, V2 raised to gamma gets cancelled, and we are left with P1 by P1 the whole raised to gamma is equal to P2 by P2 the whole raised to gamma into T2 by T1 the whole raised to gamma. Now this is P2 the whole raised to gamma minus 1 upon P1 the whole raised to gamma minus 1 is equal to T2 by T1 the whole raised to gamma. And therefore we get P2 by P1 is equal to T2 by T1 the whole raised to gamma upon gamma minus 1. So this is one conclusion we get, that how do we relate the pressures of the process to the temperatures of the process. We can also write T2 by T1 is equal to P2 by P1 the whole raised to gamma minus 1 over gamma. Now let us find out what are the changes of internal energy and enthalpy for this process. the internal energy for this process is du is equal to Cv into Tt. Now we integrate it for this process, 1 to 2 du is equal to Cv, which is a constant, integral dt 1 to 2. So we get delta U is equal to Cv into T2 minus T1. If we know the initial pressure, that is P1, the final pressure, that is P2, and if we know the initial temperature T1, using this equation we can calculate T2. Now this T2 can be replaced in this equation and we can calculate delta U. Similarly, delta H for this process is going to be equal to Cp into T2 minus T1. So, to sum up what we have learned, for an adiabatic process, dq is equal to 0. That is, no heat is given or taken in the process. Also, change in internal energy is equal to Cv into T2 minus T1. Change in enthalpy is equal to Cp into T2 minus T1. Pv raised to gamma is a constant. Also, we can say, looking at this equation, we can say P the whole raised to gamma minus 1 T the whole raised to gamma P the whole raised to gamma minus 1 is also equal to a constant. So these are the two equations that we can get. And last thing to note, that the equation of state is valid for an adiabatic process. That is all for now, guys.